like to explore solving polynomial inequalities with you. The inequality that we're going to solve will be this: x minus 3 times x minus 1 times x plus 4 is greater than 0. And to do that, I'm going to graph the polynomial function that is y equals x minus 3 times x minus 1 times x plus 4. Now, I've already graphed it, so let me pull that up for you. Here it is. And by the way, I did this on Desmos.com. It's a very easy program to use for graphing. Desmos.com. So if our task is to determine where x minus 3 times x minus 1 times x plus 4 is greater than 0, we're going to be looking on the graph for the places that the y value for this particular function is positive. In other words, where is the graph above the x-axis? So let's look right here. We see that the graph is above the x-axis. And then again, over here, the graph is above the x-axis. Let me label some of our key points. Let's see, we have a key point right here at -4, and at 1, and at 3. Those seem important for this graph. So just looking at the graph, I could say the solution to this inequality is the set of numbers between -4 and 1 and the real numbers that are greater than 3. So let's answer using interval notation. So I will say from -4 to 1, union 3 to infinity. But this graph would also help us to solve this inequality. X minus 3 times x minus 1 times x plus 4 is less than 0. Notice this time we're looking to see where the y values for the function that we have graphed are negative. In other words, where is the graph below the x-axis? Now notice right here between, or to the left of -4, and in between 1 and 3. So our solution to this inequality would be -infinity to -4, union 1 to 3. And let me point out the very critical numbers in the solution to these two inequalities. They are these: -4, 1, and 3. Those are our x-intercepts, and if we look back at the inequalities, they're the numbers that make the factors equal to 0. Let's look at another inequality. We'll now solve this one. X minus 4 squared times x plus 2 is greater than 0. And as before, let's look at the graph of the related function. So we'll look at the graph of y equals x minus 4 squared times x plus 2. And here it is. In this case, we're looking to see where the graph is above the x-axis because we want to know where the y values are positive. So looking here at the graph, notice between -2 and 4, the graph exists above the x-axis, but it doesn't exist above the axis at 4. So I'm going to just put an open circle there to remind us that it doesn't exist above right there at 4. But to the right of 4, again, it is above the x-axis and hence the y values are positive. So our solution to this inequality would be the real numbers between -2 and 4. Let me put an open circle right here at -2 to remind us it is not included in the same way 4 is not. So -2 to 4. And we also would like to include the numbers to the right of 4, so that we would have union 4 to infinity. Recall that parentheses, when used in interval notation, tell us that we're excluding that value. Let's change the inequality slightly and make it this: x minus 4 squared times x plus 2 is greater than or equal to 0. The only way in which this one will be different is we will include the numbers where the function would actually equal 0. That means we're going to include the number -2 and we're going to include the number 4. So when we're writing our solution in interval notation, we now don't need to break at 4. We'll start at -2 with brackets around the -2, and we'll move all the way to the right toward positive infinity. And our solution looks like that. I want to solve one more inequality while we have this graph up. And let's let it be this. It will be x minus 4 squared times x plus 2 is less than or equal to 0. So now I would like all of the real numbers for which this product is negative or where the product is equal to 0. Now this time we're still going to include the -2 and the +4 because the graph equals 0 there, or the function equals 0 there. But now we want to know where the graph exists below the x-axis for the y values to be negative. And notice that is here. So the solution to this inequality is the set of real numbers to the left of -2, or less than or equal to -2. And we also need to include the number 4. So let's write this out. We'll have negative infinity up to and including -2 union the number 4. Now the number 4 isn't an interval, it's just a single point. So we will put it in braces this way. So here's our solution. The interval from negative infinity up to -2 union the number 4. Notice again on these inequalities that the critical numbers for this particular problem were -2 and 4, the numbers that make each factor equal to 0. Let's look at one more by using the graph to help us. So the problem that we'll be solving is this. -0.1 times x minus 4 times 2x plus 1 times x plus 3 squared is greater than or equal to 0. And notice I already have the related function graphed. And also notice that we have the points, or I have the points labeled here that come from the factors and when they equal 0. Notice this -0.1 does not generate an x-intercept anywhere over here because it's a constant. Only those factors that contain variables will generate x-intercepts. So let's go. We're looking for where this product is greater than or equal to 0. So that is above the x-axis or on the x-axis. So let's see. We have nothing from left to right, nothing until we get to -1/2. And there the function equals 0. And then it remains positive until we get to 4. And that's our complete solution. So if we were going to answer using interval notation, we would have a solution of -1/2 to 4. And oops, I almost overlooked -3. Do you see that -3 is where the function actually equals 0. We have a point actually on the x-axis right here. So -3 also must be included. So let's write that first. Usually we write our solution from smallest to biggest. So I'm going to squeeze that in right here. It is -3 union the closed interval from -1/2 to 4. And now this problem is finished. Now its related inequality, let's do -0.1 times x minus 4 times 2x plus 1 times x plus 3 squared. Let's say we want to know where it's less than or equal to 0. Now we want to include any number that gives a result that is negative or equal to 0. So we're looking to see where the graph is below the x-axis or on the x-axis. So that means we have values starting down here. Let's see, at -3 it equals 0. Notice we do want it to equal 0. We're going to include that, and we'll include this point right here at -1/2. And then let's see, it goes negative again to the right of 4. So our solution presented using interval notation would be -∞ up to -1/2. Notice I did not even break at -3 because -3 is included, and we also are including numbers on to the right of -3 and to the left of -3. But we did need to break at -1/2. Then we have a union, and we need the numbers greater than or equal to 4. So 4 to infinity, and we have it solved. Now the question is this: can we solve these without looking at a graph? And the answer is absolutely yes. Let me point out that the only places where the graph changes from positive to negative or negative to positive are those numbers where the function actually equals 0. So those are going to be critical values when we're solving these without looking at a graph. So let's look at one. So let's solve this one. X minus 5 times x minus 8 is greater than 0. And I'm going to do that by drawing a number line and doing what's called interval testing. We're going to put the critical values on our number line, and they are the numbers that make this product is equal to 0. And of course, they are 5 and 8. Now, our job is to determine within each interval whether those numbers would make the product positive or negative, because they will all do the same thing. So, for example, if we choose in the interval to the right of 8, we choose the number 9. If you pop 9 into the product, you'll have 9 minus 5 times 9 minus 8. And I don't really even care what the value is. I see that it's 4, but it's a positive 4 times a positive 1. And the result of a positive times a positive is a positive. So no matter what number I were to choose to the right of 8, the result would be positive. So I'm going to put a plus right here. Now let's choose a number in between 5 and 8. And remember, it doesn't matter what you choose. You can choose 7 or you could choose 5.1739. But I want the arithmetic to be nice for me, so I'm going to just choose 7. So I'm testing this interval right here. 7 minus 5 times 7 minus 8 is a positive 2 times a negative 1. So that's a positive times a negative, and the result is negative. So let's write that. And finally, I choose a number. I choose a number to the left of 5. And I'm going to choose 0. If it's in an interval, I usually choose that one. So I would have 0. So I'm testing this interval right here. So I have 0 minus 5 times 0 minus 8. That is a negative 5 times a negative 8. And again, I only care about the fact that it's a negative times a negative, where the result is positive. So now I know where the product is positive and where the product is negative. The question was, where is the product greater than 0? That is, where is it positive? And I can just look at my number line, and I see that to the left of 5, it's positive, and to the right of 8, it's positive. So my solution using interval notation would be negative infinity up to 5, union 8 to infinity. And this is the essence of how we'll solve our polynomial inequalities. Let's move to a problem that looks like this. Solve, and it will be x minus 6 squared times x minus 18 is less than 0. So notice it's factored, and there's a 0 on one side, and as soon as it looks like that, we can go right to our interval testing. So I'm going to draw my number line. My critical values are the numbers that make each factor equal to 0. So my critical values are 6 and 18. And now my job is to interval test. I choose a number to the right of 18, like 20. I pop 20 into my factors, and I have 20 minus 6 squared times 20 minus 18. I have a positive number squared, that's a positive, times another positive, and the result is positive. So let me put a plus right here. I choose a number in between 6 and 18. I'll choose 10. So I have 10 minus 6 squared times 10 minus 18. I have a positive number squared, that's a positive, times 10 minus 18, that's a negative, and a positive times a negative is a negative. So let's put a minus right here. And finally, to the left of 6, I choose a number like 0. 0 minus 6 squared times 0 minus 18 means I have a positive number times a negative number, and again the result is negative. So I can look at my number line with the results above it. I'm looking for where the product is negative. I do not want to include the numbers that make it equal to 0, so I'm going to exclude 6 and exclude 18. But I want to include the numbers to the left of 6 and in between 6 and 18. So our solution set for this problem would be negative infinity to 6. Make sure you break at 6. Union 6 to 18. And this one's finished. Let's solve another one. Here's my polynomial inequality. It's x cubed plus 7x squared minus 4x is greater than or equal to 28. Notice a couple things. One, there's not a 0 on one side, and also it's not factored. We need to transform this inequality so that it will have both of those things. So let's start by getting a 0 on one side. That means I'm subtracting 28. So my inequality will become x cubed plus 7x squared minus 4x minus 28 is greater than or equal to 0. Notice there's no common factor, but there are 4 terms, so I'm going to factor by grouping. I'm going to take out my x squared from the first 2 terms, and I'm going to take out a negative 4 from my second 2 terms. And you see that I have a common factor here of x plus 7. So our next line will look like x plus 7 times x squared minus 4 is greater than or equal to 0. I have the difference of 2 squares, so I can continue factoring. X plus 7 times x plus 2 times x minus 2 is greater than or equal to 0. And now my polynomial inequality is the way I want it to look. There's a 0 on one side and a factored expression on the other side. And now we go to our interval testing. I'm going to put the critical values on my number line. I have a -7, a -2, and a +2. And I test numbers in each interval. I'm going to start to the right of 2, pick a number like 10. And as you practice with these, you'll probably be able to see some of them in your head. Like if you pop in 10 in the first factor, we have a positive. 10 plus 2 is positive. 10 minus 2 is positive. And I have a product of 3 positive expressions, and that gives me a positive. Let's pop in 0 in between -2 and 2. 0 popped into that expression gives me a positive times another positive times, notice, a negative, because 0 minus 2 would be -2. So if I have a positive times a negative, the result is negative. In between -7 and -2, we'll test -5. Putting -5 into the first factor gives us a positive number. -5 in the second factor gives you a negative number. And -5 in the third factor gives you a negative number. So I would have a positive times a negative, which is a positive. And to the left of -7, we're going to test a number like -10. If we put -10 in, we would have a negative times a negative times a negative, which results in a negative result. Notice this time we want to know where the product is positive or equal to 0. So we're going to include these critical values, 2, -2, and -7. And we want to include the intervals where the product is positive. So our solution would look like the closed interval from -7 to -2, union 2 to infinity. And when you're doing this kind of a problem, do show the number line with the results. That's part of the work that you would want to show when you're solving a polynomial inequality. Let's do one more. It will be this. We're going to solve x cubed plus 9x is less than or equal to 6x squared. This one, like the previous one, is not set equal to 0. So let's start there. We'll subtract 6x squared, and let's put it in the middle so it will be easier for factoring. So we have x cubed minus 6x squared plus 9x is less than or equal to 0. We have a common factor of x, so let's take that out. We have a trinomial that factors into x minus 3 times x minus 3. Oh, notice we have x minus 3 as a factor twice, so let's write it a little bit nicer. Let's make it x times the quantity x minus 3 squared is less than or equal to 0. And I'm going to draw my number line for interval testing. Our numbers are 0 and 3. And let's test a number to the right of 3, like 4. 4 makes the first factor positive, the second factor positive, and a positive times a positive is positive. Between 0 and 3, we could test 1. 1 gives us a positive. 1 gives us a negative number, but it's being squared, so that's also positive. Positive times a positive again is positive. And to the left of 0, let's put in -5. That means we would have a negative number, and we'd have a negative number that is again being squared, so that's positive. A negative times a positive is a negative. And we're looking to see where this product is negative or equal to 0. So again, I'm going to include the endpoints, the 0 and the 3, because they make that product equal to 0. And we want to know where the product is less than 0. That means where it's negative. So right here, the number is to the left of 0. So our solution set for this one would be negative infinity up to and including 0, union, and now we just have that number 3. Remember, it's not an interval, so we're just going to put a braces around it, and it looks like this. Negative infinity up to 0, union 3. And we have this one solved. I want to point out one more thing about these two problems. And here it is. Notice in this first problem here on the left, the exponents were a 1, and a 1. And if you look down here at the number line, the intervals bounced back and forth between negative and positive, positive and negative. On the problem on the right, the exponents were a 1 and a 2. And the critical value that came from the factor that was being squared was 3. Let's come down here on the number line. And on either side of the 3, the signs were the same. It turns out when the critical value comes from a factor that's raised to an odd power, the signs on either side of that critical value will be different. If the critical value comes from a factor that's raised to an even power, the signs on either side will stay the same. Let me give you one last problem to illustrate that point. This will be our problem. X times x plus 4 squared times x plus 10 cubed times 7 minus x is less than or equal to 0. Notice it already has a 0 on one side, and on the other side it's factored. So let's draw our number line, and we'll put our critical values on. For the first factor, I would get a critical value of 0. My second factor gives me a critical value of negative 4. And our next factor, raised to the third power, will give us a critical value of negative 10. And to the right, we have 7 minus x is equal to 0. That gives us a critical value of 7. So I'm going to interval test using one interval, and then I'm going to use the exponent to determine the results for the other intervals, and I'll show you what I mean. Let's pick a number to the right of 7, like 8. So we're going to pop 8 in, and that means we would have a 8 times 8 plus 4 squared times 8 plus 10 cubed times 7 minus 8. And that means we have a positive times a positive squared times a positive cubed times a negative, and the result there would be negative. Now, I certainly could go through each interval and pick a number and do the interval testing, and there is absolutely nothing wrong with that. But let me point out what we can do using the exponents. Right here, do you see the exponent is a 1 on the 7 minus x? That means the critical value of 7 that comes from this factor will be the place where the sign changes from plus to minus or minus to plus. So to the right of 7, I have a minus. That means to the left, I would have a plus. 0 comes from this factor right here. Its exponent is a 1. That is also odd. So the sign will change again. So from plus, it will become minus. Whoop. Negative 4 comes from this factor right here. Notice its exponent is even. That means the signs on either side of this negative 4 will stay the same. So because that's a minus, this sign in this interval will also be a minus. Let's put that in. And our negative 10 comes from this factor. Its exponent is odd. So again, the signs will change. I have a negative here. That means this one would become positive. And I have finished my interval testing. We could definitely double check if you wanted, just to make sure. We can just pick any interval we like. Right in here, I could pick a number like -7. Pop -7 in, you'd have -7 times -7 plus 4 squared times -7 plus 10 cubed times 7 minus -7. You'd have a negative times a positive times a positive times a positive. The result is negative, and it matches what we had. So it's kind of handy to know that about the exponents. Let's finish writing our solution to this problem. We were looking for where it's less than or equal to 0. That means we're going to include the numbers that make the product 0, which is -10, -4, 0, and 7. And we want the intervals where the product is negative, so -10 to -4, -4 to 0, and 7 to infinity. So our solution in interval notation would be -10 to 0. Notice I did not have to break at -4 because it was included. Union 7 to infinity. And this problem is done.